In this video, we're going to be looking at hypothesis tests and confidence interval options in logistic regression. So we're not going to spend a lot of time in this class kind of doing these kinds of things, but we'll kind of briefly introduce some of the basics for this. So the first is going to be kind of this hypothesis test for determining parameter significance, determining whether or not this parameter is not equal to 0, and therefore this predictor is actually adding predictive power into the model. So if we're testing whether the parameter is different from 0, though we could also do it for some other value as well, but 0 would be kind of the common choice, because that would just mean the particular predictor variable is adding predictive power if the parameter is not equal to 0. It can still be done in logistic, but just keep in mind that now we're actually going to be doing a z-test rather than a t-test. And I think the book actually calls this a walled test as the heading, which I would just call it a z-test. A walled test would just be essentially a chi-square test, which is really the same functional thing in this context, but a z-test to me is the more straightforward title for what this is. And so what we would do here is find the difference between our observed statistic, our observed parameter estimate, against the null hypothesized parameter, which is likely going to be 0 when we're doing this kind of test, and then just dividing that by the standard error to get a z-score or z-value. So the only difference, the reason that we're calling this a z-test is because this statistic right here can actually be approximated by a normal distribution, and we can call it a z-score because our estimate for the standard deviation of beta hat is actually pretty precise because we're working with proportions data rather than kind of continuous measurable data in the response. And without going further into it, all you need to know is that when we're working with kind of a proportion and estimating the variability in proportion data, we don't really have the same estimation errors that we have when we're working with measurable data. We don't need a t-distribution and a t-correction in this case. So long story short, in this context, we can approximate this test statistic with approximately following a normal distribution 0, 1. Again, same kind of conclusions we'd make. We would get a z-score, we could calculate a p-value, and we could determine how often we would see a discrepancy this large or larger by random chance. Because if our p-value is really low, right, so if we get not the best normal distribution I've ever made, but if we get a test statistic, a z-value that's kind of like out here somewhere, what that's kind of telling us is that if the parameter really was 0, then the statistics that we observed, the beta hat value that we observed, is pretty unusual to happen by random chance. So whenever we get kind of this extreme p-value, it means that we have evidence that maybe this parameter is not actually equal to 0, that this variable is actually adding predictive power as a predictor in this model. Whenever our p-value is a bit higher, it means that we're seeing a beta hat value that is more reasonably, something that I could see. If the parameter really was 0, it means that it's plausible this predictor isn't actually adding anything to our model, and that we just kind of observed a little bit of random chance correlation going on here. So same kind of conclusions we'd make with ordinary least squares, testing of the parameters there as well. A likelihood ratio test is kind of like the f-test equivalent for logistic regression. So likelihood ratio tests are used to kind of compare two models, one that's a little bit fuller than the other, to determine if the fuller model is actually explaining a statistically significant amount of predictive power beyond what the kind of smaller model is already predicting. So our null hypothesis in a likelihood ratio test kind of follows what we do in an F-test to compare models, where we're testing the additional parameters that exist in the larger model that don't exist in the smaller model. So these are kind of like the additional parameters in larger model not already in smaller model. So we want to know if this larger model, by adding these additional parameters, by adding these additional predictor variables, is adding something, is explaining a statistically significant amount of additional variation, additional kind of prediction in the response. Or is the amount of predictive power that's being added kind of what we'd expect by random chance, by simply adding more parameters, by just adding some complexity to the model to try to fit it better. And so the test statistic that we calculate with a likelihood ratio test is called the deviance. It's abbreviated with a D. And we calculate the deviance with this expression down here, minus 2 times the log of the likelihood function of the model using the null model divided by the model using the full model. So we're not really unpacking the mathematics here. It's just not something that our course is super interested in. We just kind of want to introduce logistic regression. We want to talk about when we use it and just give it kind of enough background so that you know that there's some method behind what we're doing, but not spending a lot of time with the mathematics, because that's just not kind of a big goal of this course. But we're calculating this thing called the deviance. The deviance is kind of like the F test that we've talked about for model comparison, where essentially we're just kind of comparing the likelihood of the data under each model. It can be calculated by this expression here at the end as well. And this statistic is going to be modeled with a chi-square distribution. So if the null model is just as good as the full model, and the full model just has extraneous predictors being added, then this value right here should follow a chi-square distribution. If the full model is explaining additional predictive power, and the additional predictors that are being added to the model actually do something, then it's not going to follow a chi-square distribution. We're going to get a value that's higher than we would expect by random chance. So therefore, what we do is just kind of compare our deviance statistic to the chi-square distribution to see how reasonable it is. How often would we observe a value as far or farther than we did by random chance if the null were true? So again, kind of this same idea that I'm sure you've done many times, either in our class or in other classes before. There's this chi-square distribution that looks kind of like this. We find our particular deviance value. We find how likely we are to observe a deviance value this far or farther by random chance if the null were true. And we get this thing called a p-value. And whenever our p-value is really low, it means that the null hypothesis probably isn't true. That we have some evidence against it, because this is a pretty unusual result to observe if it were true. Whenever our p-value is bigger, like maybe our deviance value is over here somewhere, then our p-value is going to be all of this range right here. And maybe now the null hypothesis is a little bit more plausible, that this is something that could happen if the null hypothesis were true, and the fuller model isn't actually doing anything more. It's not adding any more predictive power to this model. So again, just know how to kind of interpret that p-value when we run this test in R, and that's what it's kind of representing for us. To kind of demonstrate each of these things, so the z-test for parameters as well as the likelihood ratio test, we're going to quickly look at an example that's also presented in the book, where we're predicting the likelihood of coronary heart disease using LDL cholesterol as a predictor. So here's the data kind of modeled, by the way. So here we have low density lipoprotein cholesterol, so LDL cholesterol. And an observation that we might make here is that as LDL cholesterol increases, we tend to see the likelihood of coronary heart disease also increase as well. I mean, certainly there's a lot of variability here. There's people on both sides, but in general, as this value is increasing, we seem to see this likelihood being a little bit better, a little bit higher for folks to have coronary heart disease than it would be for LDL cholesterol levels down here. Okay, so the null hypothesis that we might test here is whether this actually matters. Like, is this just maybe some sampling variability that we just kind of happen to see this result because we only have a sample, and maybe if we collected more data, this relationship would just go away, and we just kind of see a flat line as this model, as kind of the true model here, or is this enough of a change to say that yes, this is actually mattering? This predictor is actually predicting the likelihood of coronary heart disease. So if we create a model, we create this kind of logistic model, and then we run a summary, or in this case, I think it's just the coefficients was produced here. We can get an estimate for the intercept and slope value, and we also get the z-test result for the slope as well to be 1.04 to the -7. So that's telling us right there we have some very strong evidence that this is not explained well by random chance if it didn't matter. Therefore, LDL probably is an actual predictor here, that it's probably kind of gaining us some predictive power for coronary heart disease likelihood. We can also do an example where we compare models using a likelihood ratio test. So let's say that we take this LDL model, kind of this simple model, and compare it to the model where I just include all the other predictors available, which is going to be these 1, 2, 3, 4, 5, 6, 7, 8 additional predictor variables. And I can do a likelihood ratio test to compare these two models to determine whether or not I have evidence that at least one of these predictors is contributing to this prediction as well, or the null hypothesis would be that all of them don't matter. They're all the parameters are just zero. All the predictors aren't actually predicting anything if I add them. So I can run a likelihood ratio test using actually the ANOVA function again, so just the ANOVA of the two model names. The only difference is I just need to add a test argument to identify that I'm doing a likelihood ratio test now with these two models. I get a result that looks very similar to what I've seen before. When I do an f-test for model comparison, I get a p-value. This is the lowest p-value that R reports in a summary table, meaning that I have some very strong evidence that there is at least one predictor here that is contributing to this model, that I'm explaining a lot more of the variability in coronary heart disease likelihood by having this information added into a model. Now, it doesn't necessarily mean that all of these predictors are contributing, but I do have evidence that at least one of them is contributing. Honestly, a good chance that probably several of them are contributing. But I would have to kind of look at them one by one to kind of decide which predictors are actually contributing, possibly doing some kind of stepwise selection method to choose a best model if that was my goal. All right, and then just a quick word about confidence intervals for parameters. We're not really going to focus much on this. I will kind of mention this one's very easy. A confidence interval for a parameter. You can just use confint to get a confidence interval for a particular beta value, which is just going to be calculated with a z-interval using the appropriate kind of z-score for that particular confidence level and the standard error of beta hat as well. Now you can actually do a confidence interval for the expected value of y at a particular x. It's mathematically a bit more tedious. The derivation we're not going to talk about, but I just did kind of want to just mention that you can do that. Mathematically, it would be represented by this or these expressions right here for the lower bound and upper bound. I think there's an example kind of walked through in the book. We're not going to really do it on any questions either on the homework or on the exam, other than just me just mentioning this is a thing that you could do if you wanted to. I will also mention you can't really do prediction intervals when you're doing logistic regression. You can do a confidence interval, for the expected value of y given x, or the expected value of y at any particular x value. But there's no such thing as a prediction interval because I'm not capturing actual observations with an interval, because all the observations are either 0 or 1. So I can only sensibly make a confidence interval for what that true probability that y equals 1 is, but there's no such thing as a prediction interval when I'm modeling binary data, because there is no range of observations except for the ones that are just literally at 0 and 1. So I just thought I would mention that as well there.